The Works of Archimedes, on the Sphere and Cylinder, Book 1, Propositions 21 to 44. This is the second video in this series of videos that I'm putting together, giving some analysis of some of the works of Archimedes. The source material for these videos is Thomas Heath's translation of Archimedes, and this video is the second instalment of On the Sphere and Cylinder, Book 1. In the first video, I covered propositions 1 to 20 from On the Sphere and Cylinder, Book 1, and in this video, I'll cover the propositions 21 to 44, which will then bring us to the end of this particular book. Much of the hard work of this book has already been done by this stage. Now, in propositions 21 to 44, it's time for Archimedes to really start to apply some of the results derived in the first half of On the Sphere and Cylinder. It will be necessary, in order to keep things to a reasonable length, to sometimes use more algebraic arguments in this video, though I will try to use geometric methods as much as possible and within reason. In the second half of On the Sphere and the Cylinder, Book 1, we see how Archimedes manages to bring together all of the seemingly random results that have been obtained in the first part and build them up to a climax, and Archimedes has a knack for doing this. There are some really incredible results in this part which we might take for granted and possibly overlook the ways in which these results have been derived by some of the greatest thinkers in history. The remaining propositions of On the Sphere and Cylinder, Book 1, that is, propositions 21 to 44, can be roughly split into two categories. Propositions 21 to 34 are concerned mostly with surface areas and volumes of spheres, and shapes inscribed in and circumscribed about spheres. The propositions from 35 to 44 are mostly concerned with segments and sectors of spheres and shapes inscribed in and circumscribed about these segments and sectors. It will quickly become evident as we go through the propositions in the second half of On the Sphere and Cylinder why certain propositions which seemed unusual at first glance were proved in the first half. We will also see that most of the hard work has been done in that first half, and now it's time for Archimedes to reap some of the rewards. In many cases, there won't actually be much for me to say regarding the demonstrations of the propositions, other than a few miscellaneous comments. Sometimes the demonstrations are simply an application of one or two of the previously proved propositions, and the result just falls out. In this way, there's a great risk of overlooking just how beautiful some of the propositions are that have been proved, and it's easy also to overlook just how much work has been done in building up to that result. I personally find the propositions 21 onwards to be fascinating, and it can be tempting to fly through these propositions, but I'd recommend the reader take it steady, not because the proofs are necessarily difficult to follow. They may not be difficult to follow, but that says nothing for how difficult they were to come up with in the first place, but to take the time to fully absorb the result and what has gone into obtaining that result. In the statement of proposition 21, the angular points mentioned are the pairs of points such as B and B primed or C and C primed, which can be joined by a straight line perpendicular to the line joining the points A and A primed. The triangles ABA primed and ABF are similar since angle ABA primed is a right angle by Euclid's 2:31, and since BF is perpendicular to AA primed, so triangles ABA primed and ABF are similar by Euclid 6.8. And since BB primed and CC primed are parallel, then angles FB primed K and KCG are equal by Euclid 129. Angles FKB primed and GKC are equal by Euclid 115. And of course angles B primed FK and KGC are both right angles. Therefore, since triangles FB primed K and KCG are equiangular, then by Euclid 6.4 they're similar. The similarity of the other triangles can be shown in a similar way, which gives rise to the series of equal ratios as shown. And then using Euclid 5.12 the result follows immediately. The proof of proposition 22 works in more or less the same way as proposition 21. And in proposition 23, that the number of vertices of the regular polygon inscribed in the great circle ABC of the sphere is a multiple of 4 ensures that A, M, A primed and M primed are all vertices of this regular polygon, and that A primed and M primed are diameters of the circle. When the polygon and sphere are rotated, then the sides of the polygon will describe frusta of isosceles cones. These are the portions of conical surfaces that are mentioned. This proposition is simply showing that the surface area of the solid obtained when the polygon ABC is rotated about the axis AA' is less than the surface of the sphere obtained by rotating the circle ABC around the axis AA'. This is just an application of assumption 4, and of course it would be possible to show the same using another suitable pair of segments such as the segments NaN' and Na'N', or YaY' and Ya'Y'. The demonstration is very straightforward and requires no further explanation. I suppose it may be strictly necessary to show that if we know that the two halves of the hemisphere are separately greater than the corresponding halves of the inscribed solid, that the two halves of the sphere added together must also be greater than the two halves of the inscribed solid added together. But I hope I'll be forgiven for omitting a detailed proof of that. For proposition 24, let the surface of the cone ABB' plus the surface of the frustum BB'C', be equal to a circle of radius r. Then using the results of proposition 14 and proposition 16 we have as shown. And so by Euclid 12.2 and Euclid 5.11 we obtain as shown. That is, the surface of the cone ABB' to the surface of frustum BB'C' is equal to BA times a half BB' to BC times a half BB' plus CC'. Then by componendo we obtain as shown. And thus we have. But by Euclid 5.7, the circle of radius r to the surface of the frustum BB'C' is equal to the circle of radius r to the circle of radius the square root of BC times a half BB' plus CC', since the surface of BB'C' is equal to the circle of radius the square root of BC times a half BB' plus CC', giving as shown. Therefore by Euclid 12.2, r is such that the square on r is equal to BA times a half BB' plus BC times a half BB' plus CC'. That is, the square on r is equal to BA times BB' plus a half CC', since BA is equal to BC. Of course, it would be a legitimate question to ask at this stage, is it possible to construct, using straight lines and circles, a circle whose radius is effectively the square root of the sum of the squares of the radii of the two other circles? And the answer to this is yes. It's possible using a few propositions from Euclid. I won't cover this in this video, but I have another video on my channel which gives an example of finding the square root using geometrical techniques, and this may shed some light on which direction to possibly go in to construct such a circle. Anyway, returning to the proof, continuing in the way just shown will give the results. The proof of this proposition, proposition 25, presents no real difficulties. However, the steps shown on screen can be explained roughly as follows. Construct a rectangle with base of length equal to BB' plus CC' plus YY', and a rectangle with base equal in length to AA', and each with height equal to AB. Then we have by Euclid 6.1 that the rectangle on BB' plus CC' plus YY' and AB to the rectangle on AA' and AB is equal to BB' plus CC' plus YY' to AA'. Therefore, by Euclid 5.11 and using the result of proposition 21, we have that the right-hand side is equal to A'B to AB. Similarly, construct a rectangle with base equal in length to A'B and a second rectangle with base equal in length to AB, and each with height equal to AA'. Then again by Euclid 6.1, rectangle on A'B and AA' to the rectangle on AB and AA' is equal to A'B to AB. And thus by Euclid 5.11 we obtain as shown. And obviously the rectangle on AA' and AB is equal to the rectangle on AB and AA', and so by Euclid 5.9 the rectangle on BB' plus CC' to YY' and AB is equal to the rectangle on A'B and AA'. And in more modern notation this is AB times BB' plus CC' plus YY' is equal to AA' times A'B. And we also need to remember at the very end of this proof that a primed b is less than AA primed, and so the square on AA primed is greater than the rectangle on AA primed and A primed b. Archimedes starts out the proof of proposition 26 by constructing a solid inscribed in the sphere. And what I find particularly interesting is the way that in proposition 26 Archimedes divides up the solid that he forms inside the sphere. It's certainly not the most obvious way of creating such a shape inside the sphere, and it may have been a more natural and obvious choice to split the inscribed shape into solid frusta rather than the shapes that Archimedes uses, but without having worked out the details myself, this could possibly have led to more complicated formulae. Through this particular way of dividing up the solid inscribed in the sphere, we can start to see many of the earlier proved propositions being applied, and it starts to become clear why those propositions were being proved, and we start to get a bit of a taste of how Archimedes is able to lay the groundwork which will later form the basis of the proofs of some brilliant results. The demonstration of this particular proposition is, however, fairly straightforward. I also don't have anything to add regarding proposition 27. Again, the demonstration is straightforward. The circle which is described about the polygon in proposition 28 is not used until in the next proposition. The proof of this proposition is nothing more than an application of assumption 4, therefore nothing further needs to be added. There's nothing to comment on either for proposition 29 other than it's in the proof of this proposition rather than the previous proposition that the circle described about the polygon is required. The result of proposition 30 can be compared with the result of proposition 25. And in this proposition, triangles ABA primed and APO are similar triangles, and P is the midpoint of the line AB, and so A primed B is equal to twice OP. Again, there's nothing for me to add to the demonstration of proposition 31. And the squares of the radii of the circles R and S described in the demonstration of proposition 32 are given by propositions 29 and 24 respectively. Since R and S are circles, then circles are to one another as the squares on their radii, then by a slight modification of Euclid's 12.2 we obtain that the ratio of R to S is equal to the square on radius of R to the square on the radius of S. Therefore, by propositions 29 and 24, we obtain the ratio as shown. AB times BB primed plus CC primed plus and so on can be thought of as the area of a rectangle with sides equal in length to uppercase AB and uppercase BB primed plus CC primed and so on. And similarly for lowercase ab times BB primed plus CC primed and so on. Then since the inscribed polygon and circumscribed polygon are similar, then uppercase AB to lowercase ab is equal to uppercase BB primed to lowercase BB primed, and so on. Therefore the rectangles are similar. Moreover, by Euclid 6.20, similar polygons are to one another as the duplicate ratio of that which the corresponding side has to the corresponding side. Since therefore uppercase AB and lowercase ab are corresponding sides, then uppercase AB times BB primed plus CC primed and so on to lowercase ab times BB primed plus CC primed and so on is equal to uppercase AB squared to lowercase ab squared. And so by Euclid 5.11 we have that R to S is equal to uppercase AB squared to lowercase ab squared. And therefore the surface of the circumscribed solid to the surface of the inscribed solid is equal to uppercase ab squared to lowercase ab squared as required. The equality of ratios uppercase ab to lowercase ab is equal to OA to P follows from definition 1 of Euclid 6. Similar rectilineal figures have their angles severally equal and the sides about the equal angles proportional. The inscribed and circumscribed polygons are similar by assumption. However, to show that V and W are in the triplicate ratio of uppercase ab to lowercase ab, that is, in the triplicate ratio of the radii of their bases, we need to show that V and W are similar. the ratio uppercase AB to lowercase ab equals OA to P unfortunately does not immediately demonstrate the similarity of V and W, since uppercase AB and lowercase ab are not the radii of the respective bases of V and W, though of course by the construction of V and W, OA and P are the respective heights. Thus it's necessary to show that the ratio uppercase AB to lowercase ab is indeed equal to the ratio of the radius of the base of V to the radius of the base of W. Indeed, the equality, the ratio of V to W is equal to uppercase AB cubed to lowercase ab cubed, follows easily enough using modern algebraic techniques, and not much indication is given in the book as to how exactly this equality of ratios comes about. So let's have a look at how this might be justified using more geometrical considerations. We know using part 1 of the demonstration of this proposition that the square and radius of r to the square and the radius of s is equal to the square on uppercase AB to the square on lowercase ab, since we've already shown that r to s is equal to uppercase AB squared to lowercase ab squared. In the demonstration of this proposition on page 39, it appears to be taken as a given that this ratio leads to the ratio the radius of r to the radius of s is equal to uppercase AB to lowercase ab, from which follows the similarity of V and W, and hence the result. However, I want to show this in more detail. Now at a point O, construct a line OX of length equal to uppercase AB using Euclid 1.2, and cut off from the line OX using Euclid 6.10 a length OY such that the radius of r to the radius of s is equal to OX to OY. And note that the radius of s is smaller than the radius of r, and so OY must be less than OX. We need to show that OY is equal in length to lowercase ab. So now on the radius of s, construct a rectangle with height equal to the square on the radius of r, and similarly construct on OY a rectangle with height equal to the height of the square on OX. Then by Euclid 6.1 we have that the square on the radius of r to the rectangle on the radius of s and the radius of r is equal to the radius of r to the radius of s, and the square on OX to the rectangle on OY and OX is equal to OX to OY. Therefore by Euclid 5.11 we have that the square on the radius of r to the rectangle on the radius of s and the radius of r is equal to the square on OX to the rectangle on OY and OX. In a similar way, we can obtain the equality that the rectangle on the radius of r and the radius of s to the square on the radius of s is equal to the rectangle on OX and OY to the square on OY. And therefore by Euclid 5.22 we have the square on the radius of r to the square on the radius of s is equal to the square on OX to the square on OY. And since we know that the square on the radius of r to the square on the radius of s is equal to the square on uppercase AB to the square on lowercase ab, then by Euclid 5.11 we have that the square on OX to the square on OY is equal to the square on uppercase AB to the square on lowercase ab. And since OX was constructed equal in length to uppercase AB, then the square on OX is equal to the square on uppercase AB. Therefore by Euclid 5.9 we have that the square on OY is equal to the square on lowercase ab, and therefore OY is equal in length to AB. Therefore we have that if the square on the radius of r to the square on the radius of s is equal to the square on uppercase AB to the square on lowercase ab, then we also have that the radius of r to the radius of s is equal to uppercase AB to lowercase ab. Therefore, the radius of the base of V to the radius of the base of W is equal to uppercase AB to lowercase ab. But we also have that the height of V to the height of W is equal to uppercase AB to lowercase ab, as already shown. And so by Euclid 5.11 we have the radius of the base of V to the radius of the base of W is equal to the height of V to the height of W. And so by definition 24 of Euclid 11, except using radius instead of diameter, cones V and W are similar. So by Euclid 12.12, similar cones are to one another as the triplicate ratio of the diameters, or in this case the radius, on their bases. Therefore, the ratio of v to w is equal to the cube on the radius of the base of v to the cube on the radius of the base of w, which of course gives the ratio of v to w is equal to the cube on the radius of r to the cube on the radius of s. But since the radius of r to the radius of s is equal to uppercase AB to lowercase ab, then by using similar geometric arguments as shown earlier, we have that the cube on the radius of r to the cube on the radius of s is equal to uppercase AB cubed to lowercase ab cubed. Therefore, by Euclid 5.11, we have the result, v to w is equal to uppercase AB cubed to lowercase ab cubed. This proposition, proposition 33, is a major result, the surface area of a sphere. We're also told on page 18 of the introduction, Archimedes is said to have requested his friends and relatives to place upon his tomb a representation of a cylinder circumscribing a sphere within it, together with an inscription giving the ratio which the cylinder bears to the sphere, from which we may infer that he himself regarded the discovery of this ratio on the sphere and cylinder 133 and 34 as his greatest achievement. The mean proportional constructed in this proposition can be constructed using Euclid 6.13, and that the side of the outer to the side of the inner is less than beta to delta implies that the square on the side of the outer to the square on the side of the inner is less than beta squared to delta squared can be shown using a similar approach to that which I outlined in relation to proposition 5 in the first video. In part 2 of the demonstration, note that beta to gamma is less than c to the surface of the sphere, which is the opposite way round to in part 1 of the demonstration of this proposition. The statement of proposition 34 says that any sphere is equal to 4 times the cone which has its base equal to the greatest circle in the sphere and its height equal to the radius of the sphere. However, it may be noteworthy that what is shown in this proof is that any sphere is equal to the cone with base equal to 4 times the greatest circle in the sphere and with height equal to the radius of the sphere. This is the cone V which is constructed. And of course 4 times the cone which has base equal to the greatest circle in the sphere and height equal to the radius of the sphere, and the cone with base equal to 4 times the greatest circle in the sphere and height equal to the radius of the sphere are equal volumes. However, they are still two different things. It wouldn't be difficult to show that the volumes are equal, but it would possibly be something that still needed to be shown at some point. The equality of the two volumes would be very straightforward, almost trivial to show, using modern algebraic techniques. The arithmetic means delta and epsilon are such that beta is less than delta is less than epsilon is less than gamma, and the difference of beta and delta is equal to the difference of delta and epsilon, which is in turn equal to the difference of epsilon and gamma. The construction of suitable beta and gamma can be done using proposition 2, and the similar polygons constructed inscribed in and circumscribed about the great circle can be done using proposition 3. And since we know that by construction, the side of the outer polygon to the side of the inner polygon is less than beta to delta, then using a similar approach to the one that I gave in relation to proposition 5 in the previous video, with a suitable extension to cubes, it can be shown that the cube on the side of the outer polygon to the cube on the side of the inner polygon is less than beta cubed to delta cubed. And since the volumes of the solids are in the triplicate ratio of their sides by proposition 32, then the volume of the outer solid to the volume of the inner solid is equal to the cube on the side of the outer polygon to the cube on the side of the inner polygon. And so the volume of the outer solid to the volume of the inner solid is less than beta cubed to delta cubed. As for the justification of beta cubed to delta cubed is less than beta to gamma, I won't give a full justification using geometrical methods for this, but I will give a justification for the inequality beta squared to delta squared is less than beta to epsilon. And from this it can be seen at least how the inequality involving cubics may be obtained through a suitable generalization. At a point O, construct a straight line OE of length equal to epsilon, and cut off lengths OB and OD equal in length to beta and delta respectively. Then since beta, delta and epsilon are in what we may call arithmetic progression, then BD and DE are equal in length. Now by Euclid's 2.4, we have that the square on OD is equal to the square on OB plus the square on BD plus twice the rectangle on OB and BD. Also, by Euclid 2.1, we have that the rectangle with base OE and height equal to OB is equal to the square on OB plus the rectangle on OB and BD plus the rectangle on OB and DE. However, since the rectangle on OB and BD has height and base respectively equal to the height and base of the rectangle on OB and DE, then these rectangles are equal. Therefore, the rectangle with base OE and height equal to OB is equal to the square on OB plus twice the rectangle on OB and BD. Therefore, it's obvious that the square on OD is greater than the rectangle on OE and OB. So by Euclid 5.8, we have that the square on OB to the square on OD is less than the square on OB to the rectangle on OE and OB. But the square on OB and the rectangle on OE and OB have the same height, and so by Euclid 6.1 we have that the square on OB to the rectangle on OE and OB is equal to OB to OE. Thus by Euclid 5.13 we obtain that the square on OB to the square on OD is less than OB to OE, and therefore we have that beta squared to delta squared is less than beta to epsilon. Although a geometric approach is clearly possible, it will be quite tedious to carry out. An algebraic argument for beta cubed to delta cubed is less than beta to gamma might go as shown. And a further approach is given in the book and is credited to Eutocius. And part 2 of the proof proceeds along very similar lines to part 1. And Archimedes now turns his attention towards segments and sectors of spheres, and goes on to prove similar propositions concerning these segments and sectors to the propositions proved for spheres in propositions 21 to 34. Many of the remaining propositions are very similar to the propositions already seen, and the proofs are also very similar. Therefore, it won't be necessary for me to go into too much detail with these proofs, and in fact some propositions will require little or even no further explanation. The proof of proposition 35 is very similar to the proof of proposition 24. No further explanation is needed for the demonstration of proposition 36, and this proposition can be compared with the result of proposition 23. In proposition 37, we have that the triangles ALM and ALA primed are similar by Euclid 6.8, and therefore AA primed to AL is equal to AL to AM, and hence AA primed times AM is equal to AL squared, the justification of which follows similar lines of reasoning to that given in my explanation of proposition 25. And in fact, proposition 37 can be seen to be very similar in nature to proposition 25. The demonstration of proposition 38 is straightforward, and this proposition can be compared to the result of proposition 26. In proposition 39, that uppercase LT is greater than lowercase lt can be seen by considering the triangle T lowercase l uppercase L. L is a point on the radius O lowercase l produced, and so since lowercase lt is a tangent to the circle at lowercase l uppercase L and lowercase lt must be perpendicular, and so angle T lowercase l uppercase L is a right angle. The right angle in a right angled triangle must be the greatest angle, and so by Euclid 119, the side opposite the right angle, uppercase LT, must be the longest side of the triangle, and in particular, uppercase LT is greater in length than lowercase lt. For proposition 40, that the rectangle AB times BB primed plus CC primed plus KK primed plus a half LL primed is equal to the rectangle A primed B times AM, follows from the equality of the ratios BB primed plus CC primed plus LM to AM equals A primed B to BA from proposition 22, and then using a similar approach to that I outlined for the demonstration of proposition 25. Also note LM primed is used in proposition 22 and a half LL primed is used in this proposition, and that LM is equal to a half LL primed. Triangles uppercase AML primed and lowercase AML primed have a common angle. Angle uppercase AML primed is equal to angle lowercase AML primed. Since uppercase AL primed and lowercase AL primed are parallel, then by Euclid 128, angles uppercase MAL primed and lowercase MAL primed are equal, and also angles uppercase AML primed and lowercase AML primed are equal. Thus the triangles are equiangular, and so, by Euclid 6.4 and definition 1 of book 6, they're also similar. And since n is the midpoint of uppercase AB, and ON is parallel to A primed B, then again triangles ABA primed and ANO are similar, and hence A primed B is twice the length of ON. Moreover, since ON is a radius of the inner circle, twice ON must be equal in length to lowercase AA primed, since lowercase AA primed is the diameter of the inner circle. We have therefore that uppercase A primed B is equal to lowercase AA primed, so by Euclid 5.7, uppercase A primed B to uppercase AM is equal to lowercase AA primed to uppercase AM. And since uppercase AM is greater than lowercase am, then by Euclid 5.8, lowercase AA primed to uppercase am is less than lowercase AA primed to lowercase am. Therefore, by Euclid 5.13, uppercase A primed B to uppercase am is less than lowercase AA primed to lowercase am. And by using similar constructions, similar to the approach I gave for proposition 25, it's easily shown that uppercase A primed B squared to uppercase A primed B times uppercase AM is less than lowercase AA primed squared to lowercase am times lowercase AA primed. And since uppercase A primed B is equal to lowercase AA primed, then uppercase A primed B squared is equal to lowercase AA primed squared. And so by a variation of Euclid 5.10, it follows that uppercase A primed B times uppercase AM is greater than lowercase am times lowercase AA primed. And since lowercase AA primed is bisected at m, then by Euclid's 2.3, the rectangle on lowercase AA primed and lowercase am is equal to the rectangle on lowercase am and lowercase ma primed plus the square on lowercase am. But lowercase am and lowercase ma primed are both equal in length to lowercase ml primed, and so the rectangle on lowercase am and lowercase ma primed is equal to the square on lowercase ml primed. Therefore, lowercase am times lowercase aa primed is equal to the square on lowercase am plus the square on lowercase ml primed. But by Euclid 147, and since triangle lowercase aml primed is a right-angled triangle, the square on lowercase am plus the square on lowercase ml primed is equal to the square on lowercase al primed. Therefore, lowercase am times lowercase aa primed is equal to the square on lowercase al primed. And therefore, uppercase a primed b times uppercase am is greater than lowercase al primed squared. And since the surface of the solid figure is equal to the circle with radius whose square is equal to uppercase a primed b times uppercase am, and since circles are to one another as the squares on their radii, we have that the surface of the solid figure to the circle of radius lowercase al primed is equal to uppercase a primed b times uppercase am to lowercase al primed squared. Then it follows that since uppercase a primed b times uppercase am is greater than lowercase al primed squared, by a variation of Euclid 5.14, that the surface of the solid figure is greater than the circle of radius lowercase al primed. That the rectangles in proposition 41 are in the ratio uppercase ab squared to lowercase ab squared can be justified in a similar way to that which I outlined in the demonstration of proposition 32. Also that the volume of the cone with base s and height on, and the volume of the cone with base lowercase s and height o lowercase n are in the ratio uppercase AB cubed to lowercase ab cubed, can also be justified using a similar approach to that which was outlined in Proposition 32. Propositions 42 and 43 are straightforward and don't require any further explanation. The result of Proposition 44 can be compared to the result of Proposition 34, and many of the techniques used in the demonstration of the current proposition are very similar to the techniques used in the demonstration of Proposition 34 as well. For Part 1, we know by Proposition 39 that uppercase V plus the cone on OLL primed is greater than S. And so, since the inequality uppercase V plus the cone OLL primed to lowercase v plus cone OLL primed is less than S to R holds under the assumption that S is greater than R, then we cannot have that lowercase v plus the cone OLL primed is equal to R, since then we would have by Euclid 5.8 that uppercase V plus the cone OLL primed to lowercase v plus cone OLL primed is greater than S to R. Nor can we have that lowercase v plus cone OLL primed is less than R, since then we would have again by Euclid 5.8 that uppercase V plus cone OLL primed to lowercase v plus cone OLL primed is greater than uppercase V plus cone OLL primed to R. And also by Euclid 5.8, uppercase V plus cone OLL primed to R is greater than S to R, since uppercase V plus cone OLL primed is greater than S. And so we have that uppercase V plus cone OLL primed to lowercase v plus cone OLL primed is greater than S to R, and therefore we must have that lowercase v plus cone OLL primed is greater than R. Also for Part 1, the impossibility is due to the inequality lowercase v plus cone OLL primed greater than R, since we know that R is equal to the cone with base equal to the surface of the segment lowercase LAL primed and height equal to the radius of the sphere. However, by Proposition 42 and Proposition 43 if necessary, the surface of the segment is equal to the circle with radius lowercase al. Thus, R is equal to the cone with base equal to the circle with radius lowercase al and height equal to the radius of the sphere, which, by Proposition 38, the corollary, and Proposition 43 if needed, must be greater than lowercase v plus cone OLL primed. Similarly for Part 2 of the demonstration, where the impossibility is due to the inequality uppercase v plus cone OLL primed is less than R, which contradicts the result of Proposition 40. It's interesting to note that in On the Sphere and Cylinder, formulae for surface areas and volumes of various shapes are always expressed in terms of the relation that that area or volume has to some other area or volume. For example, in Proposition 33, the surface of any sphere is equal to 4 times the greatest circle in it. Archimedes is able to establish this formula even if we don't actually have a way of finding the area of a circle. That is, if there is no specific formula known for finding the area of a circle. Thus we're able to speak of an area or a volume and so on, even if we have no specific way of measuring the size of that area or volume, and we can go further and establish various relations that that area or volume has with other areas and volumes. The focus in Archimedes, and in Greek geometry more generally, is much more on the relations of areas with other areas and volumes with other volumes and so on. Moreover, areas and volumes are not here identified with numbers, and for that matter, neither are lengths or angles and so on. So I'm not suggesting by this that the ancient Greeks didn't measure lengths and so on using numbers, or at least multiples of some suitable measuring unit, in a similar way to which we do nowadays. I'm sure they did. The definitions at the start of Book 7 of Euclid's Elements suggest that some similarity was considered between some numbers and certain geometrical objects, such as planes and solids, though these plane and solid numbers appear to be more to do with certain types of what we would now recognise as positive integers, since a number is defined in Euclid 7 to be a multitude composed of units. And of course, this definition may not be used by other Greek authors. So I'm not saying that this identification of lengths and so on with numbers is not implied in some way in Archimedes, but this aspect does not feature explicitly in On the Sphere and Cylinder. Even in Measurement of a Circle, where we see a derivation of an approximation of pi, unless I've overlooked something, it doesn't appear that even here lengths are identified with numbers. We merely see the ratios of lengths as a certain type of magnitude, compared to, but not necessarily equated with, ratios of numbers as another type of magnitude. We also have to bear in mind that the concept of number, as understood by the ancient Greeks, does not coincide with the modern day notion of number. We now are quite comfortable dealing with, say, irrational numbers in modern mathematics, but these were a source of great difficulty in ancient Greece, and indeed, irrationals have been a source of difficulty in more recent times. It's interesting to note that in Euclid's Elements, books 7, 8 and 9 deal with numbers, but then when incommensurables make an appearance in book 10, Euclid changes to general magnitudes or lines, since it may be that two magnitudes are incommensurable and hence that their ratio is irrational, and therefore the ratio of these two magnitudes cannot be expressed as a ratio of numbers. Thus, even if the ancient Greeks did sometimes identify lengths and so on with numbers, it doesn't seem that this identification would be considered in anything like the same way that we would consider it now, and, moreover, the identification will be at best partial. That is, some lengths can be represented by numbers, whereas others cannot be. Note that in Euclid Book 10 we have the following propositions. Proposition 5. Commensurable magnitudes have to one another the ratio which a number has to a number. Proposition 6. If two magnitudes have to one another the ratio which a number has to a number, the magnitudes will be commensurable. Proposition 7. Incommensurable magnitudes have not to one another the ratio which a number has to a number. And Proposition 8. If two magnitudes have not to one another the ratio which a number has to a number, the magnitudes will be incommensurable. Of course, these propositions assume the definition of number given by Euclid in the definitions at the start of Book 7, and which was mentioned earlier in the video. Also note that it's common to see derived a relation between, say, the surface area of a certain open cylinder and the area of a certain circle, but we rarely, if ever, see the relation between the surface area of the curved surface of a cylinder and the area of, say, a rectangle, though this would be quite common in contemporary mathematics and geometry. That is, the areas, volumes and so on of certain shapes will often be compared with the areas and volumes of some particular types of shapes, but not others. There is an exception to this, evidently, in Measurement of a Circle, where the area of a circle is compared to the area of a right-angled triangle K, with sides containing the right angle of lengths equal to the radius and circumference of the circle respectively. This is very unusual though, because there would be a serious issue with the construction of the given triangle. The construction of such a triangle appears to be comparable to the problem of squaring the circle. It doesn't seem that the impossibility of constructing, using only straight lines and circles, of a particular shape would necessitate the denial of its existence in Greek geometry, and it seems not, at least in Archimedes. But indeed, this may vary from one Greek geometer to another, and which types of constructions were accepted by them. But certainly the existence of, say, a square with equal area to a circle would be accepted in contemporary mathematics and geometry without the need of constructing such a square. Of course, Archimedes does not construct the triangle K mentioned in Measurement of a Circle, but nevertheless seems to assume its existence. It does appear that Archimedes accepted more complex constructions, as can be seen, for example, in his work on spirals, also to be found in Heath's book. Therefore, in these videos, I've made a deliberate effort to avoid using what we would now accept as fairly standard formulae for finding surface areas and volumes, and instead to try to work with the various relations and, wherever possible, to use straight line and circle constructions as typified in Euclid's Elements, though I have allowed myself to use the more modern notation as used by Heath to keep things to a reasonable length. Clearly, many of the propositions that are proved in On the Sphere and Cylinder are obvious results, when the standard formulae are considered and modern algebraic techniques are used, and it may be that the results that Archimedes obtains may seem much less impressive when these modern techniques are applied, and if this is the case, then it's very unfortunate. I think it would be a serious mistake to underestimate the significance of the results obtained by Archimedes by comparing them to elementary results of contemporary mathematics and geometry. That brings us to the end of On the Sphere and Cylinder Book 1, and to the end of this video. I'm hoping at some point to continue this series of videos on the works of Archimedes, but I don't know when they'll appear, so keep an eye out for them. Please remember to subscribe and hit the like button, and please share this video with anyone you think might be interested. Thanks for watching.